Welcome to the Monday seminar, everyone. I am happy to host again this week. The Monday seminar, as you probably know, grew out of two different ERC-funded projects, one by me, the TECTONIC project, and another run by Massimo Coco and a group of people called the FEAR project. They're both projects connected, very closely to earthquake physics. And so we started doing this in 2020 during the pandemic and realized it was a really valuable thing for our community and for ourselves, lots of interest. And so we're continuing to do that. Really happy today to be joined by Alexis Cartwright-Taylor. And she's going to talk about this title that you can see here. I would just encourage people we'd like everyone to mute themselves right now. If you want to jump in with a point of clarification or something, please do that as we go, and then save detailed questions for the discussion at the end. One of the nice things about this format is the opportunity to have an extended discussion. And so we'll do that at the end, and we really encourage people to write down questions if they have to, prepare themselves to join in a discussion and with questions led by Alexis. So nice to see you, Alexis. Please take over. Thank you for joining us.
Thanks, Chris. Thanks for inviting me. It's really nice to be invited to speak to all you guys. Okay, so I am going to present some work that we've been doing that combines in situ X-ray imaging of rock deformation with acoustic monitoring. And I'm going to present results from a pair of triaxial compression experiments that we conducted at the Diamond Light Source to understand if changing the stress field, in this case by varying the sample loading protocol, might help to suppress seismicity and how the microstructural damage might differ between the two samples. So hopefully I'm going to show you that loading under a constant rate of acoustic emission, so this stress time evolution in blue here, and this AE event rate evolution here in orange. We loaded the sample at a constant strain rate to start with until we had enough acoustic emission events to run the control, and then we managed to stabilize failure and extend the strain softening period in order to capture a whole series of images, microstructural images of X-ray images of fault weakening and failure. Sorry, sample weakening, fault evolution, and failure. And we're going to compare this with a constant strain rate experiment to understand what happens when in the microstructure when you extend the strain softening region and stabilize fault development with the acoustic emission event rate control, and see how if this type of control might help us to minimize induced seismicity and improve on current risk management strategies that we currently have. So I'm going to go right back to basics and probably preaching this to the converted here, but for the sake of some early career people, induced seismicity are earthquakes induced by human subsurface activities that add or remove mass from the subsurface, and thus changing the stress field in the Earth's crust. And they can take the form of extraction, for example, hydrocarbon recovery, or geothermal, hot geothermal water recovery, fluid injection, so hydraulic fracturing, fluid injection for enhanced geothermal systems, wastewater disposal, injection of CO2 or hydrogen or compressed air, and then also mining operations for extraction of critical minerals, and also even reservoir impoundment, where we're loading the surface and then the subsurface is experiencing stress changes. And induced seismicity can occur in areas even in areas with low levels of previous seismicity. And one of the reasons for that is because the crust is already critically pre-stressed due to natural tectonic processes. And for that reason, also induced seismic magnitude may be large, even though the human activity causing it may itself only involve small changes in stress, and these large events may potentially lead to significant damage on the surface, and maybe in some cases even injury or loss of life. And the triggering mechanisms for these events are pretty much case dependent, but are mainly around poroelastic stress transfer, seismic elastic stress transfer, and aseismic slip. So, for example, in a fluid injection scenario, the near wellbore region will experience poroelastic changes from changes in pore fluid pressure, and that will then extend into the far field in terms of poroelastic stress transfer, and then even extending down connected faults, larger faults, or even unconnected faults due to changes in the stress field. So this is an example from wastewater injection in Oklahoma. And what happens when you inject in this near field area is that we move our Moore's circle, so the relationship between the shear stress and the normal stress moves our Moore's circle. So this is A. So this situation is this black semicircle, and this situation, once we've increased the pore fluid pressure, is this grey semicircle, and it shifts it to the left, such that faults oriented in this region would be likely to reactivate because they're reaching the Coulomb stress failure threshold. So in addition to the poroelastic stresses, then seismic elastic stress transfer, that is where the elastic waves from induced events or natural events can trigger sequences after the initial induced event. And then aseismic slip, that's where you have small aseismic slip events on a fault that can then accumulate over time, and then eventually the fault will rupture seismically. And so all these mechanisms perturb the state of effective stress by changing the shear and normal stresses or the pore fluid pressure, or both, on a given fault plane, bringing it closer to reactivation. Sorry for my chest. So we've seen that both in injection and extraction scenarios, the actual pressure change extends quite far beyond the region of where you're injecting or extracting your fluids, and our stress and strain changes occur even further away from that. And actually, some micro-seismicity, so reactivation of pre-existing small fractures, and some local deformation, such as subsidence or uplift, is actually quite useful for monitoring the state of the reservoir during the operation. So you can track your injected plume, for example. You can understand the stress state of the reservoir, and so small events and can often be very useful for monitoring. But obviously then, if we come into contact with a large fault and the pressure changes are large enough, or the stress changes are large enough to reactivate that fault, then obviously we could maybe end up with a notable seismic event, so local magnitudes more than 3, which will often be felt and raise concern in local communities, or even at the extreme, leading to complete cessation of the operation. So, for example, the UK fracking moratorium, where magnitude 2.9 event led to complete cessation of all fracking operations in the UK. And this could be disastrous for our net zero carbon operations. And minor faults with displacements below the resolution of seismic surveys, so for example, displacements less than 10 meters, are of particular concern, as we don't know where they are in the subsurface. We can't map them because they're below the seismic resolution. So how do we manage the risk of these induced events? Well, there's the main way we do it is through these traffic light systems that are currently based on preset event magnitude thresholds. So ops continue in green when they're below one particular threshold. They're modified in orange, in amber, when they're below second threshold, and then they're completely stopped when they're above this second threshold. And these thresholds are quite low. This threshold between the modification and the stopping is generally around a local magnitude of 2 to avoid public concern and discontent. However, these systems are based on extreme events only, and they can be unreliable if the reactive controls are evoked too late in the process. So your magnitudes can, in some cases, continue to increase after the operations have been stopped, and potentially leading to, obviously, concern in the local communities or catastrophic even societal or economic effects. So, for example, we have examples from these are enhanced geothermal systems where we had injection in Sources-sur-Forêt in France, where the events spread out away from the injection wells, and then even after the injection was stopped, that was when the largest events occurred, and eventually local magnitudes reached 2.9 and caused public concern. In Basel, in Switzerland, they actually had intense seismicity in the first 6 days, up to local magnitudes of 2.6. They stopped the injection, and then a few hours later, there was a magnitude 3.4 event, and then 3 more magnitudes, events with magnitude greater than 3 occurred in the next sort of 50 odd days, in the next month or so, 2 months. And they had to abandon this project because the citizen anxiety was considerable. We'll generally there's some discussion about alternative criteria for regulatory control, and various systems have been proposed. So, for example, varying the injection pressures and rates continuously instead of waiting for the thresholds, maybe based on geophysical observations rather than magnitude or ground motion thresholds. Other people have suggested probabilistic thresholds, which include velocity uncertainties and site effects. So one of the earliest risk management protocols deployed in mining operations involved monitoring the frequency of event. So when they were monitoring the micro-seismicity here, they found 2 categories of event, one that was correlated with the volume of coal extracted, and one that only occurred immediately prior to a rock outburst. And so they maintained a threshold event rate of these outburst precursor events, and when it was exceeded, they deployed pulse firing stress release techniques, so reactive control, and that allowed the mine to be worked for more than 4 years without any major outbursts. Apologies for my lack of checking this slide before I presented to you. So basically, they did evacuate the mine for some time at these points, and this study was done by Peter Stiles in 1987. So this success, along with some modelling evidence showing that mitigation on fluid pressures and elastic stresses can be effective over long distances at short periods of time, brings us some optimism that adaptive traffic light systems could effectively manage operations. And so our motivation for this study was to understand how event rate control can help to manage induced seismicity. And so we designed this comparative laboratory study of loading controls. And we were following previous work. So failure in the lab has previously been controlled with feedback control to maintain a constant acoustic emission event rate. So feedback control on the loading. And the idea is that by feeding back to maintain a constant event rate, deformation can be slowed in the approach to failure, and fault development can be stabilized. And this allowed David Lochner and colleagues to kind of obtain the first in situ images of quasi-static fault nucleation through inversion of arrival time data into locations of AE hypercenters. So you can see here before peak stress, we have our microcracks distributed. So this is A here, distributed uniformly through the sample, and then we have at peak stress nucleation of an emergent, nascent and emergent asymmetric fault plane, which then during the weakening phase propagates through the sample until it becomes sample sized, and the rock fails completely. And then if you compare this with a constant strain rate experiment, what we see here is that during distributed deformation, our AE event rate increases in a exponential manner, and then our whole process of fault nucleation and propagation occurs in this very short period of time, where there's rapid acceleration of acoustic emissions and this very short period of strain softening. So further studies have deployed this protocol to assess spatiotemporal characteristics of acoustic emissions linked to rock deformation, also variations in rupture velocity between the two events, all based on acoustic emission characteristics. And we've also used it in this study, so I'm going to present work that is currently in review, and we've also published some of the work as well. So we've used this method to achieve suitable time resolution in the underlying deformation process in order to allow us to image the fault nucleation process with X-rays. And even though it's been shown this method, constant acoustic emission event rate control, has been shown to empirically control failure, the mechanism by which it does so has not been explained in previous work. So, so we are proposing that fracture mechanics linking acoustic emission event rate with stress intensity may explain why this runaway instability is prevented under a constant AE event rate. And so this here is Charles' law for subcritical crack growth velocity, and this is V, and this VC is the critical crack growth, so the rupture velocity at dynamic failure, the system size rupture velocity, and that's related. So the crack growth velocity is related to the critical crack growth velocity and the stress intensity. So this is the stress intensity, and this is the critical stress intensity required for rupture. So that's the fracture toughness, that's the material property. And it's related to these two parameters by this exponent n, which is the stress corrosion index. And this is usually much greater than 2 for rocks. And so this implies, this relationship, Charles's law, implies remarkably non-linear behavior. And actually what Meredith and Atkinson found in some experiments is that the acoustic emission event rate is similarly related to the stress intensity by this power law, and values for n are remarkably similar. So stress intensity here is related to the stress and the square root of the crack length for a single tensile crack growing in an infinite medium. This y is a dimensionless geometric factor. And so what we can take from this is that the AE event rate is an indirect measure of the crack growth velocity or damage rate. And this nonlinear behavior here suggests that by maintaining the AE event rate in a very narrow range, approximately constant, the stress intensity is also maintained constant within an even narrower range, according to Charles' law, thereby explaining the remarkably fine control on the stability of deformation. So if control is lost, Charles' law predicts a power law acceleration in AE event rate with a singularity at the dynamic failure time. And this is consistent, that is consistent with the constant strain rate deformation. So our hypothesis is that constant AE event rate control will lead to our ability and control of the stress intensity at a constant level, control of the damage rate at a constant level, and therefore promotes subcritical failure. Okay, so this is our mechanical data from our comparative study. So we've got here our two loading protocols. So we've got our constant strain rate in orange here with our CT scan times presented as the orange circles. And then in blue here, we've got our constant acoustic emission event rate. And again, this was loaded at a constant strain rate up until the point over here where we started to detect sufficient acoustic emissions to run the control. So that occurred shortly after yield around here. And then from then on, we managed to maintain very low event rates, one AE event per second, but obviously it fluctuated between 0 and 2. So 1 AE event rate plus or minus 1. And we deformed Clashak sandstone. We deformed it under saturated conditions with a pore fluid pressure of 5 MPa, effective pressure of 20 MPa, and at room temperature. And the AE event rate control allowed us to slow the deformation down sufficiently to capture these 20-odd micro-CT volumes in the strain softening region. And based on what I've just mentioned about the fracture mechanics, I will also present a new model for the mechanism of the stabilization of the runaway stability using the
Alexis, can I ask you a question on this figure?
Yeah.
Yeah, because I am pretty much, because when you show here the plot of the differential stress versus time, it looks like that most of the loading part is pretty much linear, which would be elasticity driven. How much differ from a real rock in which I would see a plasticity range before failure?
Oh, no, this is a real rock. This is a real rock. It was just very stiff. And so this is also a real rock. It's a bit less stiff, but you can see this sort of compactive region here, and then our we start to get yield around here, and then our event rate control takes over. So these are both real rocks, and then the model I will describe later. We have a model that maps this stress time evolution very nicely.
I wasn't clear actually to say real rock. I would say a real fault zone material that might differ from a caps rock or an host rock.
Oh, I see. So Clashak sandstone, it is a fault rock material. Our particular samples were quite well cemented. So if there was some more fractured samples, then potentially, or more porous samples, then potentially this behavior might be a little different. But Clashak sandstone is a sort of reservoir analog sandstone for the North Sea. So that's one of the reasons we used it. But obviously, does that clarify?
Thanks.
Okay, no problem.
Thanks.
Okay. Okay, so in order to conduct these experiments with our X-ray imaging, we had to build an X-ray transparent deformation cell with acoustic emissions monitoring and integrate a feedback control system into it. So this is our cell, Store Milne, we've called it, and the sample sits here in our aluminium pressure vessel. The rest of the cell is made of titanium, and our AE sensors are located axially above and below the sample. The sample is 10 millimeters in diameter and 25 millimeters long. This is our Clashak sandstone showing its faulted. This is the AE event rate controlled experiment showing this faulted sample. And then here it is on the beamline at the diamond light source. And this is where the X-ray beam comes in. And then the camera is over here somewhere. So in schematic, we have the cell, and this is connected to our fluid pumps. So this is our ram pressure pump with the blue lines here. This is our confining pressure going into the pressure vessel, and this is our pore fluid pressure going into the sample there. And then we have an LVDT to measure the axial displacement of the sample and allow us to, and this feeds back into our control laptop to allow us to maintain control with, displacement control of the sample. And the pressure sensor, so this is an external pressure sensor connected between the ram pump and the ram. And that also travels back into our control laptop to allow us to load the sample under load control. And then our AE sensors connect through our periamps to our AE hit counter, which then goes into our control laptop and allows us to control the RAM with constant acoustic emission event rate. Sorry. Okay, so I'm going to deviate slightly from the main point of the story, which is this comparative study, and just focus in on the results from the constant acoustic emission event rate experiment, because this is what we found. We managed to capture these images of the microstructure during weakening. And to our knowledge, it's the first time that anyone has successfully monitored acoustic emissions during an in situ imaging experiment and used them to control the failure process during such a test and capture these images of fault nucleation. So just to play this video. So here we see damage accumulating in the left side of the sample. The bulk moves down towards the left side, and this shear zone localizes. Just play that again. And then we're going to zoom in. So if we zoom into the fault plane, we can really see the mechanisms by which it's happening. So we have an echelon tensile cracks. These are formed from point loading and pore emanating fractures. And that's failure of individual grains, producing dilation. And then our shear strain is accommodated by actually by crack rotation. So rotation of grain fragments, antithetic rotation, and then also antithetic sliding, so sliding perpendicular to the shear zone, which may or may not be aseismic, depending on whether these grain fragments are touching. And this rotation, it prevents tensile propagation through multiple grains. So that gives us some idea of why there might be a grain size control on failure in these small scale samples. And then we also see synthetic sliding along grain boundaries, newly formed grain boundaries and existing grain boundaries. And then eventually coherent slip occurs along this kind of proto-cataclysite that's formed as a result of grain rotation, fragmentation, and fragmentation of asperities. And you can see here there's an intrinsic correlation between between dilation, and shear strain in the damage zone, where we have tensile dilational processes and shear process all are co-occurring together with the rotations as well. So these are images of incremental 3D strain fields. And these were obtained from digital volume correlations between neighboring CT scans. So we're looking at incremental stress changes between each of the CT scans. And what we see is some strain clustering occurs once we start to see a little bit of micro-cracking. This is AE event rate in green. And then we have, once the sample is yielding, we have this kind of self-organized exploration of these candidate shear zones. So we see some localization in the strain fields of potential damage zones, and then once we get past peak stress, then the system chooses its eventual failure plane, and the spatial distribution increases along that plane, and while the strain rate decreases briefly, and then all of a sudden the strain rate increases again back, and we see micro cracking. So these pink areas are regions of localized en echelon micro cracks, and then these cracks travel up and across the sample in kind of like a cohesive zone, rather than a sort of concentrated at the propagating front of a discontinuity, and then we have coherent sliding once the asperities have broken, and the fault can slip, the shear zone can slip along its fragmented gouge. So one of the things that we could use this digital volume correlation in these 3D strain fields for was to understand whether the local slip on the fault plane releases as much, or whether the amount of energy required for local slip on the fault plane is that predicted by the bulk. And actually what we find is that we need actually less energy. So this is Jim Rice's shear fracture energy method calculation, and we have shear stress on the y-axis, relative slip on the x-axis. And actually what we see is that we have around 50% less fracture energy when we just look at the local slip from the digital volume correlation from the strain fields, from the dilation and the shear strains within this shear zone object in terms of image analysis, and then compared with the bulk estimate from the mechanical data, we have almost double. But then, of course, some local strain is dissipated off fault. So actually, we're looking at around 38% of the bulk fracture energy seems to be unaccounted for, which may be something to do with these aseismic mechanisms on the fault. So the grain crack rotation. We found, just looking at individual cracks, that the slip due to rotation for individual cracks can be as large as about 70% on average of the total observed local slip. And the other thing we saw is that the critical slip distance is smaller locally. So you need less energy, and the slip doesn't have to be so far in order to fail locally than we predict from the uniform slip model. And then so some, we're interested in understanding a bit more why that is. We haven't found an answer yet exactly. So the other thing that the 3D strain fields allowed us to look at is the relationship between the different mechanisms. So we have our compaction mechanisms dominating at the start with a little bit of competing dilation. Then we start to see, as we start to see increasing dilation, we also see a mixture of dilative and shear strain mechanisms. And we see this very strong correlation between dilation and shear all the way through deformation, with increasing contribution from shear mechanisms as we move through the strain softening phase and eventually into some degree of shear enhanced compaction during sliding. Okay, so these are, and this is consistent with acoustic emission source mechanisms from previous studies. Okay, so that was digressing to the nice, from the, after digressing to some nice images of what we found in the acoustic emission event rate experiment, we're now going back to the comparison of these loading protocols. So we wanted to test the following hypotheses: that the deformation mechanisms differed between the two loading protocols, that the constant AE event rate loading might limit maximum magnitudes or suppress amplitudes of all events, and maybe even promote aseismic deformation compared with the constant strain rate. And then we wanted to understand whether our model for our new model that captures strain hardening and softening regions, that explains how failure is stabilized post-peak by maintaining a constant subcritical stress intensity, how that maps onto the stress history for the AE event rate loading. So first of all, we're looking at the microstructures. So because of the limitations around the rupture speed and the constant strain rate experiment, we really only can compare the peak stress damage, the 2 CT scans at peak stress, and also after failure, after unloading. So here at peak stress, we see quite similar nucleation mechanisms in terms of pore emanating, point loading, and grain boundary cracks. It's mainly tensile that we observed, but there are some shear cracks, quite similar in terms of crack lengths. You might argue that there are some cracks slightly longer and slightly more open under the constant strain rate, but they're generally quite similar, these microstructures. However, there is evidence in the constant axial strain rate at peak stress of earlier localization of an echelon tensile cracks under a constant strain rate than under constant AE event rate. And you know, this localization of a shear zone really only occurred after strain softening in test B, whereas here we're seeing localization already at peak stress. And then if we look post-failure, then we can see significantly broader shear zone, some more off-fault damage. We've got more pronounced branching in test A and than in test B. And maybe some more fragmentation, a bit more gouge, some more cataclasis, more open porosity in the shear band under the dynamic loading conditions, and then for sure longer and more open in cracks than here in the constant AE event rate experiment. So if we compare then the strains, the local strains, so we've got first of all, we're looking at the mean, so the average strain evolution. So from our digital volume correlation, we take our 3D strain fields, and then we just take the average of all of the strain components in there for each tomogram. And then this is the incremental evolution here, and this is the cumulative. And this is on the left, we've got our deviatoric strain. On the right, we have our volumetric strain. And you can see that they have very similar, I mean, obviously they have similar loading protocols up until around this point here. So around just ahead of 2000 seconds. And then they continue to track the similar behavior for a short period of time. And then the constant AE event rate then prevents this critical acceleration of strain rate seen in the constant strain rate experiment.
Alexis?
Yeah.
Hi, it's Chris. Sorry to interrupt. Yeah, super interesting data. And are you going to show us AE rates also from the constant strain rate experiment? Did you record the AE rates in those as well? I assume they're much higher. But...
Yes, I will show you the AE rates. I'm coming on to that.
Okay, and then one other quick question. Maybe it comes up right here. Did both of these samples end up kind of intact at the end of your experiment? They didn't really break catastrophically? So
we didn't actually take them out of these jackets because we had these clear silicon jackets. So they both failed macroscopically. So you could see shear. Let me go back to here. So you can see the failure.
Okay.
The system size failure here. This is the AE event rate experiment, and the other experiment also had a similar shear zone visibly apparent in the sample. So they were both failed macroscopically, but whether they were still cohesive after we'd unloaded, we didn't actually take them out of the jackets to check that.
Gotcha. Okay, thank you.
No problem. Okay, so these are the So these are 2D median projections of our 3D strain fields, basically a cross strike of the eventual fault zone. And what we see here is that there is some clustering, higher intensity strain clustering, actually a bit earlier in the constant axial strain rate experiment. Unfortunately, the digital volume correlation didn't do a very great job here. I probably will have to see if I can improve on this just in this corner here. But the main point is that we see earlier localization in the strain fields as well as in the microstructure. And this constant axial strain rate experiment really didn't have any exploratory process of identifying the eventual failure plane that the constant A event rate experiment did. So this sample had kind of already decided where it was going, and then it went there. Whereas this sample, once the AE rate control set in, then it had a little bit of a think about what it was trying to do, and before it failed. But at peak stress there was some higher intensity shear strain along the eventual fault plane, just not as much as in the constant axial strain rate experiment. So here we go, coming on to our acoustic emissions. So our theory about constant acoustic emission event rates leads to a constant stress intensity and a constant crack growth velocity or damage rate. And so we might expect smaller event magnitudes. And actually that's what we do see. So we see much smaller, much larger events under the constant strain rate experiment, and hardly any large events, equivalently large events in the AE event rate controlled experiment. And when we plot the frequency distributions and we weight them by the moments, we can show that the amplitudes of all the events are suppressed for the AE event rates test compared with the constant strain rate test. So we have some evidence here for backing up our hypothesis about the constant event rate and the constant stress intensity. We also see that AE event rate control increases the seismic B value. So here, then in the constant strain rate experiment, we're looking at about 1.86. It slightly increases. And in the constant AE event rate, we've got about 1.94. And because the B value is negatively correlated with stress intensity, then if we've got a constant stress intensity, then we might expect to have a constant B value temporally. So for test B, because we had enough windows that we could analyze the evolution of the B value here in comparison with test A. Here is the temporal evolution, and you can see that within error, this B value is approximately constant. You could maybe argue the case if anyone feels differently, but yes, we can maybe say here that this fairly constant B value over time is indicative of a constant stress intensity, of the fact that the constant AE event rate maintains a constant stress intensity, subcritical stress intensity throughout the experiment. And then if we see in the B value, we're looking at a higher B value, so our larger amplitude events are suppressed. We've got an increased proportion of small to large events, and so we have a smaller stress intensity, slightly smaller stress intensity in the AE rate controlled experiment than in the constant strain rate experiment. And then the fact that these are both above 1.5 indicates that deformation is dominated by smaller events, which isn't really surprising given we've got very small samples. We're looking at grain size failure, fracturing. Okay, so one of the other things we wanted to do was to understand a little about how the proportion of seismic to aseismic deformation differs between the two tests. And so what we did here was we followed Dresenet et al.'s approach to obtain the Kostrov strain, and we divided that by the cumulative average local strain obtained from our digital, our 3D strain fields from the digital volume correlation. And so what we did here to obtain our Kostrov strain was we had to calibrate our single component sensors to a maximum potential seismic moment. Okay, so we started with looking into the microstructure. We found that the longest cracks were approximately 2 grain sizes long, so it was 800 microns. So we took source radius of largest source radius to be 400 microns. We assumed a stress drop for this largest event of 1 MPa, and then we obtained from the Kanamori-Anderson equation, we obtained our seismic scalar seismic moment, which we then used the Silver and Jordan relationship to obtain the unit length moment tensor, and excuse me, and then from there we could use the unit length moment tensor to estimate our Kostrov strain. So this would be our seismic strain proportion, this gamma AE, and then we divided that by the total amount of strain, total average amount of strain within cumulative average local strain from the 3D strain fields. And what we found was that these seismic partition factors are pretty low overall. And for the constant strain rate experiment, it's around 4%, and for the constant AE event rate experiment, it's actually an order of magnitude smaller. So we've got an order of magnitude more aseismic deformation in the AE event rate experiment. Okay, so this value here is like a lower bound, because obviously we couldn't detect all of the seismicity based on limitations on the test environment. The synchrotron hutch is very electrically noisy, and obviously there are detection limits on our AE equipment and on the sensors themselves. So so we wanted to work out a way to extrapolate back to a smallest assumed crack. And so what we did was we did our calibration step based on our largest observable crack length, and then we extrapolated back the crack population from the B value to obtain our original measurements for an extrapolated minimum source radius, and so this is from the small minimum source radius from our whole crack population, and then we extrapolated further back all the way to 100% seismic strain, which then is based on atomic scale bond breaking, which obviously is unrealistic in real rocks. And so then we found this conservative upper bound based on the smallest assumed crack that we found from pore scale measurements of Clash sandstone at a higher resolution X-ray images. They obtained this from X-ray images captured at a higher resolution than our data. And this gave us about an order of magnitude larger for the upper bound of seismic proportion of seismic strain. And again, there's about an order of magnitude difference between the two. The other thing we noticed was that we had similar corner frequencies. So we had different amplitudes here. This is the larger amplitudes in the constant strain rate experiment. This is smaller amplitudes here, but we had similar corner frequencies. So we had, and we also observed similar crack lengths in the microstructure. So we think that these different amplitudes must be related to the fact that these crack velocities are faster in the axial strain rate experiment than they are in the constant AE event rate experiment. So we're getting, for the same amount of crack opening, it's happening much faster. So the constant AE event rate slows down the crack velocity. Okay, so going back to our fracture mechanics model, I'm not going to go through all this again, but that was just to remind you of these relationships between crack velocity, subcritical crack growth velocity, AE event rate, and stress intensity. And so, this is for this original equation is for single tensile crack growing in an infinite medium. And more generally, for other loading conditions, so specifically subcritical damage during compressional failure, then we can say that we can generalize this to a Q, because we might expect the crack length exponent to differ from a half, so that the scaling constant y does actually have dimensions. And Meredith and Atkinson showed that for a special case of double torsion loading, that Q can actually equal 0. So if the growth of a crack is inhibited by loading, for example, a tensile or shear crack growing under a compressive stress field, then this leads to crack arrest and new cracks nucleating elsewhere, producing distributed deformation in the sample. And this mechanism dominates early in the loading sample and results in material hardening. And then there's a transition to hybrid fracture mechanisms later in the cycle, resulting in competing material softening, and then eventually a reduction in the rate of stress increase, and then an actual reduction in stress. And so we can express these softening and hardening processes most simply by generalizing this equation for stress intensity to have a Q for softening processes and a Q for hardening processes, and this negative sign on QH implies negative feedback on further crack growth, and that's by reducing the stress intensity as the crack length increases. So Main in 2000 assumed a linear mixture of hardening and softening processes to explain the three-stage creep law and the emergence of a power law relationship between stress and strain rate under constant stress loading, without having to invoke a separate mechanism for secondary creep. And so what we've done here is that we have changed the boundary condition from Ian changed the boundary condition from constant stress to constant event rate to constant stress intensity to respect the AE loading control protocol, and then we assume a superposition of the two hardening and softening processes. So we have under AE event rate loading, we've got our constant under constant AE event rate loading, we have constant stress intensity and constant crack growth velocity, while the stress and the crack length change with time. And so, for example, as the crack grows to system size, we need to reduce the stress to keep K and V constant and subcritical. And so for softening, we can combine these equations to get a term for the stress intensity for softening, and then we can change that with constant K into our stress evolution here. This becomes this term here, and then we can do a similar thing for hardening. So T here is a characteristic time, in this case for softening, and in this case for hardening. So then combining the two processes, our net stress for an evolving mixture of hardening and softening comes out as this equation. And this assumes that the transition between the two follows an exponential transient weighting function of the form of this, where we have our TW is a characteristic time for our transition. So our T's and our Q's are allowed to be independent variables when we're fitting the model. And we find that it captures the stress evolution of the AE event rate controlled experiment with a very high precision, and so supports our hypothesis that the system remains subcritical with a constant acoustic emission event rate. Okay, so hopefully I've convinced you with some evidence from microstructures and AE event characteristics that our subcritical and our model that our subcritical hypothesis is reasonable. And so therefore, we also propose including seismic event rate control into existing management methods. And we think that might help to better manage induced seismicity. And what's happened in the past, there have been some field studies that use such physics-based approaches in seismic risk management, and they've proved to be effective. So for example, the study by Kwiatek et al., they use near real-time seismicity information to modulate fluid injection. And that was based on, so they stopped or varied the injection rates or the pressures depending on the event magnitudes, the injected volume, and the radiated energy to maintain local magnitudes below 2 during enhanced geothermal stimulation operations in Helsinki in Finland, or near Helsinki in Finland. And actually what this had the effect of was it had the effect of maintaining the B value fairly constant. So this is the B value here in pink. And it also had the effect of ensuring that the AE event rates stay below a certain threshold as well. So this is more evidence for our hypothesis that you know, even though their study was based on magnitude thresholds, that the effect of that was to modulate the system such that it showed very similar characteristics as our laboratory seismicity as well. So our study establishes the likely mechanisms to explain why these approaches might be effective. So they basically maintain the system in a subcritical state. And we've described that with our model to describe the bulk damage in terms of hardening and softening. And we've also seen this idea from the microscopic damage and the corner frequencies that this is probably to do with slower rupture velocities. Okay, that's me. Any questions?
Mm-hmm. Wonderful. Thank you very much for a really wonderful talk, Alexis. I will invite people to unmute, join me in thanking you for a great talk, and then we can ask people to use the reaction button at the bottom of your screen. It's the easiest way to put ourselves in some kind of order, and I assume you're all experts on that, but maybe not, because people are sometimes new. This is what it looks like. If you raise your hand, it looks like this. And while other people are gathering their questions, I would like to start by, well, okay, first of all, thanking you once again for a great talk and for really a lot of interesting information. If you don't mind, maybe going back to slide, I think it was slide 13, that I had a question just about the scale of the fracture system we were looking at, because it almost looked to me, yeah, 13 I think is where I first saw it, but even 22 is fine, because it looks like, well, it was with the movie maybe. It kind of looked like the shear part of this didn't extend to the edge of the sample. Is that
This one?
Yeah, I mean, part of it is.
Oh, yeah. So there was some branching. So we had. Let's just.
It almost looked like it just ended right there. I mean, I guess I do see the bulk moving on the left-hand side, but
Yes, this also might be a function of the particular slice in the CT scan. So I think it kind of curved. So if you see here, we kind of had not much micro cracking in this kind of bottom bit at first, and then that, and in fact, hardly at all. So the micro cracking would be the strain required for the micro cracking is in pink, and so actually it kind of ended up with the micro crack. Although there was shear deformation everywhere, this damage seemed to not propagate completely down to here, because I think because of this initial damage that was accumulated. So I think it was just compacted and crushed in that region.
I see. I see.
Yeah.
Really interesting. Okay, and before we go to Massimo Coco's question, just would like to re-invite people to raise their hand, join the discussion. If you have a question, yeah, please let's hear what it is. Massimo, go ahead.
Ciao, Alexis. Thank you very much for your presentation. Very stimulating. I have two questions. The first concern the value of this subsea that you got from your experiment are relatively large with respect to the breakdown stress drop. So this means that, yeah, the previous slide, even the previous slide.
Oh, yeah.
Not this, what you have shown,
this one?
With the one with this subsea. This one, exactly.
Yeah. Mm-hmm.
So you see that you have this subsea of the order of, let's say, almost a tenth of millimeter, which is relatively large with respect to your breakdown stress drop, which, on the contrary, is relatively low. And this should have implication in the way in which you are releasing in the way in which your fracture advance.
Right. So I'm not sure I'm really
Your
following.
weakening rate is relatively low.
Are you talking about this relative slip? Or
Yeah.
Yeah. So this is in, oh yeah, so the relative slip is in microns, yes. So, well, sorry, it's in millimeters, but it's of the order of microns.
Yeah, but in any case, if you see the size of the critical slip is relatively longer than the breakdown stress drop, which means that you have a weakening rate that progressively small. This is reasonable because it might be associated to the post-failure part. But however, to me, the question is how much this might affect the capacity that you limit the magnitude of the larger event. So if you have a steeper weakening rate, you might load the portion of the shear zone, enabling larger ruptures.
I see. I think I see what you mean. So for example, if we could have compared with the constant axial strain rate, we maybe would have seen a steeper change. Is that what you're saying? Yeah. Yes. Unfortunately, yeah. I mean, unfortunately, obviously we can't. I mean, I suppose I should have maybe compared the bulk for that, but obviously because we weren't able to capture the strain fields during softening for that experiment, then we can't really compare. But I think you're right, because of the extended strain softening region. I think this whole process happens. The breakdown process happens a lot slower. Yeah. If that's what
and this is associated with my second question, because the reason why you might have relatively small peak stress is because in the experiment you don't have much strength excess, because your yield stress is almost coincident with the peak stress. You don't have a real plastic deformation, so the loading is elastic, almost 90% of the loading. And this means that the yield is almost equal to the peak, and this reduces the capacity to increase the peak. Also because you cannot further increase the normal stress. So I think that the behavior of the peak stress and the dominantly softening, of course, are to me the explanation why you have just a predominance of small magnitude earthquakes.
Okay. So you think maybe you don't need to explain it with a subcritical model? Is that what you're saying?
No, you might have both. No, the subcritical works. But to me, I was surprised by the fact that in this, because I understand and I understood since the beginning that these are real rocks, but perhaps the way in which you develop with your porous material, creating the shear band, is something intermediate between the behavior of a granular scale with a consolidated fault zone.
Yeah, sure. Yeah, I mean, obviously, it's a slightly idealized situation in the laboratory that it's not always easy to scale. Does that answer your question? I don't know if I've addressed.
Yeah.
Make some very good points, Massimo. So thank you. Appreciate that.
Thanks.
Yeah.
Yeah, well, one of the points, Alexis, is certainly going to be that, yeah, different rock types could produce different kinds of things. This technique clearly demonstrates what happens in this case. Yeah.
Yes, totally.
So please go ahead.
Yeah. Oh, and so sorry, I was just going to say we do have some experiments on some other granular rocks. So we have Brea sandstone that we're going to look into in the next wee while as well. So hopefully, and that's much more porous, much less cemented. So that will maybe show something quite different. Yep. Okay.
Gotcha. Ryan, go ahead.
Yeah. So very nice talk. You made a compelling case for why you should include something like seismicity rate, like theoretically, into something like a traffic light protocol, I think.
Yeah.
I'm curious, though, I guess my question is about how much do you think something like this can be scaled up to like a field scale sort of operation? Because a lot of, it seems like, or maybe here I have this distinction in my head when I'm thinking about field scale operations is that like for something like EGS, there's fracture stimulation, which is a tensile process and you have a growing crack. But then maybe that can encounter a fault and reactivate it in shear. That's something a bit different in terms of what you can expect for essentially how the largest earthquakes can grow out of something like that. It seems like it would be directly relevant, your results for like the fracture propagation. But do you think it could also be applied, or how could it be adapted to consider like that fault reactivation part of this?
So if I understand your question, you're asking whether we can limit if there's some interaction with a large fault zone, whether using the event rate would help to minimize that interaction essentially between the injection and the fault That is a very good question. I guess there's I guess it depends a little bit on how the stress field interacts with the I guess there'll be some delay time, for example, between the injection and the updating of the seismicity rate and then the reactive control. And so you might have some delay in your reactive control, which may or may not improve on the current issues of reactive control. The other thing is I guess if you're not aware of there being, so for example, subseismic faults, if you're not aware of a fault being there, then you maybe are controlling one set of event rates, and then an event happens that is a completely different process that then triggers a whole set of different event rates. So there might be some kind of bimodality in your event rate sort of evolution in the end. So yeah, I'm not really sure quite how to answer that, but I hope that's kind of given some thought. Do you have any thoughts?
No, I was just curious to pick your brain. I know that's it's an open-ended question, so I'm not just trying to grill you or anything, but
No,
yeah.
No, so there was a field scale study where they actually used so sorry, just find my notes on the last slide. Oh, golly, sorry, I'm just trying to move things around here. I've got my machine. So one study, Zhang et al. In 2019, they showed that you can use fatigue hydraulic fracturing. So you can use cycles of pressurization with pulse pumping, and then cycles of depressurization and relaxation to systematically reduce seismic magnitudes due to reduced breakdown pressure. So this kind of fatigue hydraulic fracturing rather than just conventional hydraulic fracturing. And you actually get a better fracture network from which to produce based on that. And then I guess if your breakdown pressures are then smaller, then potentially any faults that you're interacting with would then be reactivation would be minimized in that situation. So yeah. Oh.
Alex should know. Go ahead.
Thank you very much, Alexis. It was a very nice talk. I just had a quick question, comment. So in Lochner's experiments or in your experiment, you're stabilizing failure by actually unloading the specimen, like so you're removing stress from the specimen, and that actually makes it that you're propagating as the crack is growing, the crack is propagating at constant K, as you showed very nicely. So when you have a constant A rate, you have a constant K, and you have a constant crack velocity, and so you're stabilizing everything. But in the field, how would you really unload the system? Because our only way to work is with the pore pressure, and so it's not very obvious to me how the stress, your horizontal stresses, I mean your solid stresses would remain unchanged, and so I mean eventually we might end up to have like pumping back fluid,
Yeah, so I think that's one of the things that people are thinking about now is pulling back actually. So you inject and you eject. Maybe you adjust your injection pressures and your rates. So you reduce them as maybe your seismicity event rate or whatever parameter you're monitoring. As it goes up, you maybe reduce everything, but then eventually you might want to even extract a little bit and remove the pressure, but then that's obviously operationally quite difficult. So but I believe that there are people, there've certainly been people proposing that as a way to modulate the stress fields, but whether it's actually been tried in the field yet, I don't know. But yeah, I think that is fundamentally. I mean, the only other thing you can do is this, like this idea of pulse pumping or cyclic pumping, where you're giving the region time to relax and absorb the pressure changes before you put more in. I mean, that's kind of the only other way, I guess, you can control that.
Thank you.
No worries.
Alex, really interesting question. Yeah, so nice part of the discussion. And as we go to Georg Drazen's question, just re-invite other people who are here to join the discussion. Raise your hand, please. Let us know what you're thinking. Georg, please go ahead.
Yeah, Alexis, very nice talk. Thank you. And I think one should stress that it's certainly not easy to combine acoustic emission observations with your direct observations. So I would have two technical questions and maybe a comment that also refers to what Alex was just asking. When we did this in Helsinki, we actually tinkered around with the flow rates. So we reduced the flow rates in order to get away from what was predicted by, let's call it the Art McGar trend from his model, or the Gullis trend, and that worked. Yeah.
Okay.
But
Yeah.
but before we get too hyped about this, one should also mention, and I think that's often forgotten, this is also an economic and not just a scientific. Yeah, because we extended the injection time from the planned 2 weeks to 4 weeks, and each day was $50,000. Okay, So that's for every operator an issue.
Yeah.
Now the question that I have is, did you look at the deformation? I mean, I find it very interesting that you see that the localization behavior depends on the rate with which you load. Did you, because you have the possibility, did you look at the deformation in the wall rocks? Because I guess the total shortening of the samples, of the two samples, was about the same, right?
Yeah, yeah.
So somehow that must be accommodated by distributed deformation in the wall rock.
So we haven't done a comparison between the two. I did look at the deformation in the I didn't present it here, did I? I just showed the shear zone. So I did. So I estimated the total for our fracture energy work. I looked at the total strain dissipated off fault over the course of the experiment from the 3D volumes, and we actually had 9% from dilation and 3% from shear strain. That's the only measurement I've looked at in terms of the off fault strain. So I mean, we don't really have a kind of measure of, because we don't really have a fault as such yet in the axial strain rate experiment. We can look at the strain distribution in the whole sample, but we can't really say what's, I mean, apart from this particular area, we can't really say what's off fault and what's on fault, if you see what I mean.
Okay.
Whereas in the constant A event rate, because we have that whole fault evolution, then we can actually pick up a bit more on that. But I didn't show it here. But we do have the full 3D strain tensors, and that is included in these average values. So we're looking at, this is obviously on both, so that involves both the fault and the off fault strain. But yeah, that's a very good point. It's something to maybe look into as well, to separate the two. Thank you. That's helpful.
Thank you.
Vikram, please go ahead.
Am I audible? Yeah, thanks for the nice presentation, Alexis. Very much appreciated. I'm just curious to know or learn a little bit more about how you have physically performed the constant AE rate experiment. As because for the constant strain rate experiment, you have physical control on the pistons, but for the maintaining the constant AE rate experiments, how you have like physically what are the physical control you have in your experimental setup that actually lead you to perform this unique test?
So I mean, we basically we linked our A event rates to our RAM pressure pump with a small Arduino microcontroller, and so we had our some control software. One of our colleagues developed that for us with an Arduino microcontroller, and the event rate came in as a kind of electrical pulse. So our acquisition equipment, every time there was an event, it would just send a pulse to our microcontroller, and then in the software we just worked out a kind of rolling event rate. And then that allowed us to then send information to the RAM pump to approach or back off the sample, basically.
Okay.
Is that enough detail? Do you need more detail?
Yeah, I'm just curious to know how you have set up this experiment, and I have learned that you have like developed such kind of protocol like that actually captures the events and control the mechanical instrumental aspect. And do you have used any kind of threshold while filtering your acoustic emission data, like to eliminate the noise that actually separate out your actual events?
Yes.
And if you have any high magnitude events and low magnitude events, how these events are fits in this constant A strain rate experiment, like perhaps when you have like on the ultimate stages of breaking peak failure, you have high magnitude events, or maybe you have low magnitude events during the compaction. So how they are distributed and how you can link those phenomenon, high and low magnitude, in your experiment. Could you please explain?
Sure. So sorry, were there two parts? There were two parts to that question. Or we discussed already that. Sorry.
So I have two parts. One is like the threshold. If you have used any threshold for eliminating the noise, and then.
So we had to use quite a large gain in our experiments because the hutch is electrically noisy in the synchrotron. So we had our system set up on a stage. There's a load of stepper motors going on underneath. We actually were unable to mount our preamps on the stage. So we had our preamps kind of not far away, just on a cable about that long, which allowed us to kind of maximize the signal, because then we had 15 meters of cable traveling through underneath the floor of the hutch along with all the other electrical cables. So we had noise from the stepper motors initially, actually, in some of our experiments. So we had to shield the stepper motors, and we also shielded obviously shielded the preamps in lead and everything like that to protect them from the X-rays, which also kind of helped shield them electrically. But yes, we used a high gain. So we actually used a gain of 60 decibels in our constant strain rate experiment, and then increased it to 70 decibels in our constant AE rate experiment because of the signal to noise ratio in the acoustic data. So we actually had to kind of correct all of the amplitudes on the constant strain rate experiment. We had to correct them up as if they were acquired with a 70 decibel gain in order to compare the two. And so we used, because we were using such a large gain, we were using a threshold of about 280 millivolts on our AE thresholds for the acquisition system. But obviously, I think that could be tweaked a little bit more. It's kind of every experiment you run with this kind of setup is like a whole new learning experience every time you do an experiment. So I think there's a lot of tweaking that can be done to kind of optimize this for sure. But generally what we see is that you're right, the maximum magnitude. So there are some large magnitudes. So basically, from about 2000 seconds onwards, that's when we've got comparison between the two, because that's when the AE feedback control kicked in. And you can see here that even at just before the AE event rate control kicked in, we were getting some larger events in the constant strain rate experiment. So that might be something to do with a bit of sample variability. But then we do get significantly more large events in this region compared with the AE event rate control. During the compaction phase, it's quite similar. We get these kind of similar events, and then obviously because we used a higher gain in the AE event rate control experiment, we've got all these smaller events which are not available to us in the constant strain rate experiment. So yeah, I mean, whether this had an effect on our, I can't remember what Maria Daphne did, whether she removed all these events for our B value calculations or if she kept them in. That might contribute to our higher B value potentially. But yeah, without her, sorry, I don't think she's here, so I can't clarify that. But does that kind of answer your question, Vikram?
Yeah, that's okay. And may I know which manufacturers the AE sensors you have used in your experiment?
So that is Steve Glazer from UC Berkeley. He's the one that developed them. I think they're now with a company, but I don't know what the company is called, but if you contact Steve Glazer, I'm sure he'd be very happy to talk to you about obtaining some sensors like that.
Okay, thank you. Thanks for explaining this.
You're welcome.
Very nice talk.
Thanks.
Yeah, that's great, Alexis. Yes, it's interesting how complicated these things can be.
Yes.
Yeah, I totally appreciate your comments about the fact that there's a lot of tweaking, right, and a lot of work that's done before the experiment that you've shown us today.
Yes.
Yeah, dozens of other trial experiments that help you understand how to control everything and have the right settings on everything.
Yeah, exactly. And even just changing the event rate slightly, you know, if sometimes for a higher event rate, you might miss the peak stress and start controlling afterwards. And then sometimes if your event rate's too low, then it kicks in too early, and then you see a sudden acceleration or a deceleration in strain, and it all gets kind of muddled up. So yeah, it's a lot of trial and error and a lot of practicing in the lab to kind of make sure we've got enough, you know, in the lab at home before we go to the synchrotron, to make sure we've got the right settings for optimizing what we do in the synchrotron. So yeah. Okay.
Well, let's see, is there one more quick question or point that someone would like to make? John Rudnicki, please go ahead.
I hope it's quick, but I don't know if it will be. So my question is about your G values. So an implicit assumption in Rice's formulation is that basically the whole surface is sliding at once. And so that implies your decay length is going to be relatively large. But in your local calculation, if you were to calculate G for a small crack, it would change as the crack propagated across the specimen, presumably get larger. So maybe you explained this and I missed it. So how do you choose when to calculate the local G?
So I used basically with image processing technique, I selected the region of the shear zone itself, the high strain zone, and use that shape to estimate basically the average strain within that shape. And then I use the same shape. So obviously there would be some fewer values, but I would still use the same shape to look at the dilation as well, to have a comparison. And obviously it does change shape as you go across, but I was hoping that using the average value across the whole of the shear zone would kind of mitigate that effect.
Okay.
Yeah,
thank you. Very interesting talk.
Cool. Thank you. Appreciate your question. Cheers.
Yeah, that's a really interesting point, John. Yeah.
That's good.